had to shift all our audience to YouTube Live.
Okay, great. Let's do it.
Perfect. So, okay, perfect. So, good morning, everyone. Um, so, today we have Dr. Tapomoy Bhattacharjee. I hope
Bhattacharjee, yeah.
Bhattacharjee from NCBS, and we would be hosting him today on the SciComm Synapse. And the title for today is From Droplets to Organs, the Science and Journey in 3D Bioprinting. So 3D bioprinting has always been fascinating. And so we really wanted him to come on our platform and discuss on his journey and about 3D bioprinting. So before moving ahead, I would like my colleague to really introduce him well, so audience can have a nice introduction about the speaker.
Okay, great. Thanks for having me. Yeah.
So, hi everyone, good morning. Let me quickly introduce you all to our today's speaker. Dr. Tapomoy Bhattacharjee is an assistant professor at the National Center for Biological Sciences, Tata Institute of Fundamental Research, Bangalore, where he has been a faculty member since July 2021. He also holds an affiliated faculty position at the Center for the Physics of Biological Function, Princeton University, since April 2022, reflecting his interdisciplinary engagement across biology and physics. Dr. Bhattacharjee's academic journey spans diverse yet interconnected fields. He earned his PhD in mechanical engineering from the University of Florida in 2018 under the mentorship of Professor Thomas E. Angelini. His doctoral thesis explored cells in microgels, 3D printed microtissues, and single cell migration, marked the beginning of his innovative work at the interface of soft matter physics and cellular biology. He also holds two master's degrees from the University of Florida, one in mechanical engineering and another in chemical engineering, where he conducted thesis research on enzyme activity under magnetic fields with Professor Carlos Rinaldi. His foundational training in chemical engineering began with a Bachelor of Engineering from Jadavpur University. Prior to joining NCBS, Dr. Bhattacharjee completed a postdoctoral fellowship at the Andlinger Center for Energy and the Environment, Princeton University, under the guidance of Professor Sujit S. Datta, where he further honed his expertise in biophysical systems and soft materials. His research interests lie at the confluence of soft matter physics, biophysics, and bioengineering, with a particular focus on how physical confinement and material properties influence cellular behavior, microbial motility, and tissue growth. He has contributed to high impact research on 3D bioprinting, friction in hydrogel interfaces, and cellular dynamics in complex environments. Notable recent works include studies on bacterial colony growth under confinement. Dr. Bhattacharjee's scholarly contributions have earned him over 2,500 citations and an H-index of 22. He is a corresponding author on several publications and has been recognized with numerous awards, including Award for Outstanding Doctoral Thesis Research in Biological Physics from the American Physical Society, Outstanding Poster Awards from both Carnegie Mellon University and the Endlinger Center at Princeton. In sum, Dr. Tapomoy Bhattacharjee exemplifies interdisciplinary innovation, integrating engineering principles with biological systems to uncover fundamental insights into cellular dynamics and soft matter physics, making significant contributions to both scientific understanding and technological advancement in the life sciences. I really welcome you, sir. Thank you so much.
Thank you for such a long introduction. Thanks for having me here. Okay, so
Perfect.
maybe you can
So,
get started.
Perfect. So, before really going into the topic and discussing how everything works, I would really like you to explain our audience, in maybe short, that what does it mean by word 3D bioprinting?
Well, different people may have different versions of that. Different people may have different motivation to start putting cells in 3D.
Mhm.
Uh, some people come from the perspective of designing artificial tissues. Some
Mhm.
come from understanding, creating tumor models. Some people think
Mhm.
about simply understanding cells in 3D. So my motivation to go into this 3D bioprinting or 3D cell culture came from the fact that I wanted to know like how cells behave in complex three-dimensional environment, which
Mhm.
sort of mimics the natural niches of the cell, and what kind of environmental cues that we can give, which is in three dimension, not in on a 2D flat surfaces. I mean, one of the motivation that began when I was a PhD student was uh, we do culture cells in 2D plates and surfaces, and we learned a lot about those by looking cells on those 2D surfaces. And however, we also understand and recognize that many of those fundamental behavior of cells, metabolism, gene expression, or like even how cells interact, what ECM they produce, and all of that is very different in vivo if you look into a mouse model or something like that. Now, there is a gap between those two. Like you really do want to have the ease of using the 2D cell culture platforms. It's easy to passage, easy to grow. You can't test every single things that you do on a mouse model. It's expensive. It's hard to do. It's also ethically not very sound to go through so much of work on a mouse model. So you need something in between, which is the ease of like a 2D cell culture platforms, but also host the cells in 3D and host them to give them a 3D environment, microenvironment where they can grow, migrate. They can adhere to each other, make complexes, do cell-cell junctions, and all of that. So that's what motivated us to take this 3D culture platforms. And when you have a 3D culture platform, you also have this natural question of like, I need to place the cells in 3D. I need to pattern them because I genuinely want to know how cells interact with each other, how cells communicate with each other, how they migrate from one place to another, all of that questions. And those were motivated mostly by looking into how I should be able to place the single cells in 3D and look into their interaction, communication, all of that. But if you now take an unbiased approach and you ask yourself, what does that actually mean? What I'm trying to tell you that I would like to take the cells and I would like to put them in this like, let's say, three-dimensional space in some difficult ways or easy ways, whatever. But I want the cells to stay there. I want the cells to make communication with each other, make cell-cell junctions, produce their own ECM, reinforce environment, all of that. Uh, that is what 3D printing also is, because what does a 2D printing do? You have a command or dropping some ink into a predefined location, and you want the ink to stay there. I mean, now you can convert this ink to cells, and you can say my delivery agent is just a cell. And the cells can be dropped in different locations in 2D. That people have done a long time ago using cell spotters or like, manual spotting. Now, you do the same thing in 3 dimension. You can take the same cells and you can put them in 3 dimension, and you can let them interact with each other, communicate with each other. You get 3D printing. Now, there are many different types of 3D printing people can do. One approach is purely driven by the ideas that we know from plastic 3D printing, right? Plastic layer by layer 3D printing, where you have a molten plastic that feeds and you lay them in thin filaments on top of each other. They support their own weight. Eventually, they fuse, and you get a three-dimensional structure. Um, People do that with mammalian cells or even stem cells, bacteria as well, I think, but mostly with mammalian cells. But in those cases, what do they do is like they use a polymeric material or some sort of a bio ink, which gives the cells the rigidity. So this is one type of approach. You can do a layer by layer printing to place cells in three dimension, and then you look into them. Here, what you supply is an artificial or naturally sourced polymer that you make sure the rheological properties is so high, they are so thick, and so you can place layers of those inks on top of each other, and they will not be soggy. The other approach, what we started working on, is called either like embedding a 3D printing. So what do you do, or like submerged 3D printing? What you do is like you directly use a liquid like solid material. Basically, what you have is a 3D cell culture medium, which can go from like a liquid like property to a solid like property. And when you do have them, you can drag a nozzle and you can place the cells into a predefined location at your own choosing. And that doesn't really require you to put any external polymer or excess ACM per se. So what you can do is you can leave the cells alone in this 3D culture platforms, and you can allow them to build their own networks and build their own ECMs and build their own connections, and then become a more self-organized tissue that you would like to achieve. So these are this is a very long answer to a very short question, but yeah.
No, I think this is absolutely, what we were looking for to start this talk, because like once the foundation, so now even I also have a good foundation, and I would love to interact with you more because now I know what I am talking about. So
Right.
perfect. So what initially sparked your interest, to pursue research? And like, can you share some memorable incident maybe about during your college time, bachelor's or master's, or maybe even school? And did you ever think that you would become a PI at that time?
Well, you see, it's another job, right? So you need to do. See, you want to. There are very ideally what you would like to do for a job, right? You want to do something that you like to do,
Yeah.
something that you don't have to drag yourself to, and something that pays, and you have some sort of like independence or decision making capacity into that job. That is the kind of thing that people usually call a good job or an ideal job, whatever. For me, I think like I'm trained as a chemical engineer, so I when I was an undergrad, I have worked as an intern in oil industry. I have worked as an intern in like plastic industry. So when I mean those are short internships, but for a couple months during summer. But it kind of gives you an idea that what goes on to this real engineering jobs. And as much as I love them, I also thought that this is something that I would like to do, but I would like to have some independence where I would be doing something that I can decide or I can explore, which is very difficult to do if like a plant setting. So what I wanted to then do is like I wanted to explore like if there is any opportunities to do research in engineering, and that's how I ended up in doing research. But mostly because like I wanted to do something that I really would enjoy to do, and the fact was always like well if I don't like to do science, then sure, I will go back and do engineering again.
Absolutely.
And that was the motivation always. But eventually, what
Mm,
I realized is like, there's not much difference if you are doing really good engineering and you are doing
mm,
at least like engineering sciences. You end up
mm,
so you end up solving problems, you end up building things, you end up identifying why you can contribute. Some are for profit, some are for research. That's the only difference in this way.
mm,
Yeah.
mm, mm. Absolutely. So you mentioned that like even when I was going through your profile, I found that like your major educational degrees were in engineering, chemical
Right.
engineering and mechanical engineering.
Right.
So like what challenges did you face while transiting as an engineering student to a biophysical researcher, I would say, or during your PhD in microcells and those
Yeah,
fields?
that's interesting. See, it is hard to say there was a transition that per se
Mm-hmm.
because I mean, I started as a chemical engineering in Florida after I
Mm-hmm.
moved to Florida, but then I was working
Mm,
on magnetic nanoparticles, as you just mentioned.
mm,
During the time,
mm,
I was also interested in like all of these magnetic nanoparticles. People used to do is like induce hyperthermia in cancer
mhm,
cells, and
mm,
so I had a fair idea like how why people are doing that, what people are doing at that point. And even before that, my undergrad project in chemical engineering was also building like a delivery vehicle for not
mm,
vehicle means like a package with a polymer coating
mhm,
and stuff to deliver a drug, which I'm not going to claim I was very successful to do, but what it taught me is like how this kind of why you are doing this cancer drugs,
mm,
what is important, why it needs a
mm,
slow release, why not a burst of drug will do, all of that question I had in mind. But then when
mm,
I was finishing up this my master's in chemical engineering, and I
mm,
really wanted to do something with cells, I met my PhD advisor, and he was looking for someone who can do something like cellular mechanics in
mm,
3D. And
mm,
mechanics, I'm not a very big fan of I didn't have much knowledge of mechanics back then. My only
mm,
knowledge of mechanics was like the very standard strength of materials, or how materials bend and buckle. There's kind of
mm, mm,
questions that I had in my undergrad. So I told him like,
mm,
this is all I know. I'm happy to understand this, but I found that is very exciting because no one was ever looking into those kind of questions then. So, however, my PhD advisor Tommy Angelini, he is
mhm,
not also a biologist. Neither he was an engineer.
mm,
He was a physicist who was a professor in a mechanical engineering department who was working on physics of living systems, right? So, so in that way, it never felt like there is a department or there's a mismatch or I'm going into a new field.
mm,
Everyone was quote unquote outsiders in that way, right? So we always focused on the question, and that's how. And I carried that forward. When I went to Princeton, I started working with Professor Sujit Dada. He just moved to Caltech now, but he was in Princeton back then, and he also just started. But interestingly, Sujit also had a training in physics and mathematics, and he was a professor in chemical engineering, right? So
mm,
again, he had a very diverse training from what I had. So it was very interesting to work with in those kind of situations, and work at those kind of labs, and work with those kind of
mm,
advisors. And that, I think, shaped my way of how I see a problem. And mostly what
Mm.
I still believe is very interesting to think of a problem from the problem standpoint itself, that what do I need to do to solve this, right? And I think my background in engineering, or my very early years of training in engineering, it always have these ideas of, this is a problem, this is a hypothesis, we need to test this, or I need to solve this problem. So how do I do this? And if it takes efforts from different fields of the different other fields of science, so what we usually do is either we learn that, we master ourselves, or we collaborate with someone, we seek help from someone. But this is what we need to do, rather than focusing on what that technique or what that approach, which department it belongs to. I think it's what I personally find it interesting to stay true to the problem itself, rather than the department, or field or approach or something like that. And different problem
Okay.
may take different approaches. I mean, I'm fairly certain, like,
Absolutely.
there are questions where we had to run agent-based simulations to understand how cells behave, and there are questions
Mm.
where we had to do an ATAC-seq to understand
Mm.
nuclear
Mm.
organization. So, very different things that you need to do to, but the goal is the same. You want to answer the question. That's all it is.
Mm. Mm. I see.
Yeah.
So you mentioned about, having mentors in your lab, about your master's thesis guide, your PhD mentor, and then next in Princeton. So what advice would you like to give, to the upcoming generations of students, that how to choose a mentors and how do they shape your career?
Uh, it's very hard to actually say.
Mm.
I would say
Mm.
I was very lucky and blessed that I was at the right time at the right place, right? I mean, let's not say that I did something
Mm.
amazing and I figured
Mm.
things out. I think this is
Mm.
hard to say, right? However,
Mm.
there's
Mm.
always a thing is that I think whatever place you are at, you can always find
Mm.
ways to make it the best possible experience there. And
Mm. Mm.
I don't know if there is because it's a very interpersonal thing, that
Mm.
how your frequencies will match with what the lab does. I mean, and
Mm.
this is exactly why you would also see that uh, uh, you know uh, some people find it amazing one in one university, and some people
Mm.
don't so
Yeah.
well in that same university. They're getting the same
Mm.
resources and
Mm.
everything together, right? So it's
Mm.
not about
Mm.
finding the right lab, or finding it is finding the right connection, uh, and
Mm.
that I don't think people can do much about it. It's also because like it doesn't all there's I don't know if there is a recipe or rule book that you should check
Mm.
this, that. I think what
Mm.
I can also say that if you wherever you are, you should try to make what is the maximum I can achieve out of that. And
Mm.
if you have a question, if someone doesn't know in your lab, someone should know in your institute, someone should know in the same city, uh, and
Mm.
or now in the time of internet, if you reach out to people saying that, look, I was reading your paper, I have talked to my lab mates, I still don't think we fully understand why you are doing the way you are
Mm.
doing. uh,
Mm.
80 to 90% of time you get a response from the author
Mm.
saying that, hey, actually you might have to do this way. This is a very tiny details, it probably missed in our method sections, or something as stupid as like, well, maybe after mixing this chemical, I used to leave it on the bench
Mm.
for 20 minutes. Are you doing that?
Mm.
These things don't end up in method sections, right? You say I made a solution
Absolutely.
and I use this molar solution. but maybe it takes 20 minutes to actually dissolve, and you visibly don't know, or you visibly can't know whether it has fully dissolved or not. So
Mm,
I think that is one person can do to maximize their experience in
mm,
PhD. At the end of the day, uh, one thing I would say though is like, if you are not enjoying the PhD, then you probably
mm,
should think about like, what
mm,
can you do to make it enjoyable. I mean, it is very
mm,
personal thing. What works for
mm.
one person usually doesn't work for other. I mean, look,
True.
I can. This is like, asking someone like, you know, what do you do when you are feeling down or something, right? I mean, if you're feeling down, different people do different things. Some people
Mm,
can go
mm,
for a run. Some people can order some good food. Some people can watch a good
mm,
movie. But whatever works for you,
mm,
that you should do to get like make yourself very comfortable.
mm,
So similarly in PhD, whatever
mm,
works for you, you should do that to make the process enjoyable for you. Because at the end of the
mm,
day, the way I see it is like you're investing the prime time of your youth. Like, so if you are
mm,
planning to stay in academia, you are planning to invest like somewhere between like 8 to 10 years or even more sometimes
mm, mm, mm,
into science, and then you probably want to transition into a PI. Even the first few years in PI, it's a
mm,
good 10-15 year investment before you start seeing the fruit of your work coming, right?
mm,
Or
mm,
means like your students are starting to graduate, they are trying to build things on their own.
mm,
Until that happens, that is a 10-year 15-year time period. So if you
mm,
absolutely don't enjoy the process, then it is gonna then you cannot sustain in
mm,
that, right? So it is
mm,
super important that when you invest that much time of your youth into this process, and it's once in a
mm,
lifetime opportunity, right?
mm,
I think you should feel comfortable. That's all I should say.
mm. I see.
Yeah,
This is absolutely right. But
yeah,
as in part of academia or now you being a PI, I am definitely sure maybe in your past life, since you mentioned it takes a considerable amount of time till you become a PI.
yeah.
So, like, did you ever really looked back and saw that, mm, as you said, you invested a lot of years as well, and also like if I talk about money, then academia definitely takes a lot from you, you know. So like, what was the motivation that kept you going, and then
It
you
was never
finally.
about the money, though. I mean, I
Mm,
know
mm,
people say that, and I respect that as well,
mm,
because
mm, mm,
the industry may give you more money, uh, but
mm,
see, for me, it was never about the money itself, because I did
mm,
have a job after my BTech, and which was a really
mm,
well-paid job, and I decided to go for a master's and PhD and all of that, despite of
mm,
having that. So if
mm,
I were interested in making that money, I could have just stayed in the
mm,
job, and after this 15 years, I would
mm,
be making way more than I am making now. But the
mm,
point here is, though, I would not have the independence that I have now. So I don't
mm,
have the
mm.
ability
True
to choose what I want to do,
to
absolutely
do.
whatever I want to do, and I get paid for
Mm,
that, right? And
yes.
of course, it shouldn't be like I'm gonna go into a mad scientist mode. But what I'm saying is that
Mm,
if I it has to be coming under some ethical consideration within guidelines
mm,
and all of that. But
mm,
what I'm trying to say is, like, let's say I am working on 3D
mm,
printing and stuff like that. If tomorrow I
mm,
decide that, I'm feeling very, very interested to work
mm,
on snakes or something like that,
mm,
like how
mm,
snakes
mm,
behave or move or migrate in terrains of different things, or Or let's say I decided I'm very interested in how fish moves or fish behaves into certain environment or something. So if I mean these are two random examples that came to my mind for because of the couple papers I was reading before. But my point is I don't think if it is a very solid scientific question and I have a solid plan how I would be able to handle those questions, I don't think there is any reservation against that in academic settings. Like you don't get questioned why you are doing this if if you have a solid opinion and a question and a hypothesis and a plan. Uh, but if I'm working in, let's say, a company which makes soap, and tomorrow I decide that, well, I think we should start making biscuits because I have a great idea how to make biscuits. Um, I don't think that will be very well taken, purely for certain reasons, and the fact that uh, I have to probably go work in a biscuit company. The biscuit company will come and say like, you don't have any experience in biscuit. Why should I hire you for making biscuits, right? So you see my point. My point is, if you really value the money, you should probably value the money and only chase the money that you are looking for. And whatever profession gives you that, you should go there. If you value the independence and your own ideas, then you should come and you should not probably comparing the money side because you are getting something that is invaluable that the other people do not get. For example, you're getting credits for your own work. A lot of people in industry, they are doing like regular testing and regular work. This is a really hard work, but you know, you claim ownership of your own work and in very different way than regular jobs you get to do. So there are pros and cons, and of course, both are great professions. You have to understand whether it's for which one you would like to pursue, and whenever you make the mind, and then go for it. And I don't think there is much difference. I mean, technically, like if you're really interested in doing a job or in an industrial setting, you should definitely go for it. And I think it is important to invest time in there so you climb the ladder in that side. Otherwise, you get experience in this company, you get understand the nuances of the industry, you understand what is the demand, how to be innovative or creative in their purview. So that is what I think you should then focus on. Yeah.
Absolutely. I think this example was really nice, and not just for me, but it also would have helped others who are listening to you today to really choose what they want to do ahead, maybe after their masters or PhD.
Yeah, I mean, like, look, at the end of the day, if you don't like it, don't do it. I mean, that's as simple as that, right? Because it's none of the work, as you move into the jobs or more professional settings rather outside your school, you start to you see none of this work are easy, right? I mean, like you have to put like continuous efforts, long hours, especially if you're in academia. A lot of times things don't work out, so you have to face the failures, and most of the times you end up seeing that efforts are not working out because the sheer nature of the work. And now in those situations, if you are not comfortable, if you don't feel that, of course everyone feels the regular ups and downs of life, that is different, but I'm saying, like, if you don't find any motivation that I would be able to solve this, then you need to ask yourself that whether I should, because at the end of the day, these are the 5 or 10 years you're never going to get back.
Mm.
See,
Mm.
whatever you do, the goal is to be happy in your
Absolutely.
whole process, right? At the end of the
Mm.
day, you may have a degree or something, but if you're not happy, what does that mean, though, right?
True. True.
So,
Absolutely.
so that's my
I think
personal,
I
right? So
absolutely
yeah, I mean,
agree
there
on it.
are regular ups and downs. I mean, even like, let's say you like to play football or soccer, however you want
Mm.
to call it.
Mm.
And
Mm.
then there are days when you run and you get an ankle sprain or something. I'm sure no one enjoys an ankle sprain, but my point is, despite that pain, you still love football.
Mm.
But if you
Yes.
hate that sport,
Mm.
would you
Then
should
you
you
will.
play that? No, right? So that's the
Mm.
whole idea. I mean, regular ups and downs are there everywhere. So
Also.
yeah.
Mm. True.
Yeah.
So, starting your lab in India must have its ups and downs, and like, what was the hardest part, and how did you push through it, and then came this way?
So see,
Also
I think starting a
transiting.
lab anywhere is hard. Let's not say like it is easier somewhere. It is
Yeah,
hard.
I mean, transiting from US to India, and like changing the academic systems.
Well, okay, let me break it down into three parts.
Hmm.
One is
Hmm.
starting a lab. So, starting a lab is always hard, right? For not because like you're starting, but it also think about at this point you don't report to anyone per se for updates or for guidance or something like. I mean, of course, there are people who will guide you, like your colleagues, your institute. You have mentors, but for like you still can get bounce your ideas on other people, but you still have to be responsible for people who join your lab. So if you take that very seriously, then it's a serious responsibility that you have another 5-10 people who are depending on whose future depends on you, kind of situation, right? So that when you if that you first you get a job, then you feel great, you feel happy and all of that, but this sense of responsibility kicks in. That's a real burden, right? So then but that is why you are doing the job. So it's
Hmm.
sort of like you let that sink in and you figure out, okay, this person needs to do this work, this person needs to do that work, and that is a new thing that you're transitioning from postdoc PhDs,
Hmm.
right? So it is always hard for everyone. It's not easy anywhere. uh, Now, I was very fortunate because both of my PhD advisor and Tommy and postdoc advisor Sujit, both Tommy and Sujit, kind of seasoned me to do that because I always have mentees during my PhD and postdoc. I used to help guide whatever, maybe in a very small scale, but I did know like how to do those kind of jobs as well. So
Hmm.
while I
Hmm.
started here in a much larger scale, but I did sort of know what to expect and what not. So this is one
Hmm.
transitioning from a postdoc to an independent career kind of transition. So
Hmm.
mostly like if you in final years of your PhD or postdoc, you get to guide people all the time, so you slowly pick up how to work with other people and how to help them to actually understand their problem, and not
Hmm.
just do it for them kind of situation. So
Hmm.
so that was there. So now comes the
Hmm.
second part is like transitioning from a different country to another country. It is true
Hmm.
that I did work most of my scientific career in US. Then I moved here and I started the lab in NCBS. I would
Hmm.
I would say that transition was extremely smooth for me. And
Hmm.
I think the
Hmm.
credit fully goes to the the way NCPS works, and
Mm,
some of the infrastructure and the procedures are very similar to what I have found in US. So,
mm,
of course, there are some things that are different, but some
mm,
things, but the similarity and the attitude towards science and the approach towards science and how to set up things in the lab, all those things were extremely similar. So I did not feel much of a
mm,
difference. Now,
mm,
what was the other thing? Yeah, so the transition, right? So from one country to another. So
mm,
whenever you do a transition, like be it within the
mm,
country, from
mm,
different institute, different lab, there are always similarities, dissimilarities, right? I mean,
mm, mm,
it's, let's say, uh, I mean, many people are from India here, so I can say,
mm,
like, look, if you order biryani from two different cities, you find differences. and and that is how different things are, right? So of course, if I start
mm,
saying that, oh, this is very different than that, this is very different than that,
mm,
of course you can find that. I mean, this is the sheer nature of the whole thing. I mean,
mm,
uh, if everything was a monolith, then there was no identity of
mm.
different places. However,
True.
uh, however, there are certain things that comes at the core of the uh, procedures, right? For example, if I'm doing
Mm,
science, I want what
mm,
I want. I want a core that is there enough institutional support to help the students?
mm,
Is there enough
mm,
institutional support to kickstart my lab? Is it easy
mm,
or hard to get like instruments, chemicals in the system? And
mm, mm,
to be fairly honest about this, I think it is more or less very seamless in NCBS. So in
mm,
that
mm,
sense, I did not feel very limited by any of this. Um,
mm,
the challenge that we felt is purely non institutional, non country, non transition. It was just
mm,
the sheer nature of the time, because I started in July
mm,
2021, and after I started, the second wave of COVID came. So that was a little difficult to handle, because a lot of students, they cannot travel.
mm,
You really can't go outside in the city. You go to
mm,
the lab and you come back and you test every twice every week. So, and if you get
mm,
COVID, you get quarantine. So that
mm,
is, in all good spirit, though it's a little like upsetting to have
mm,
this burden when you are starting a lab. But
mm,
that has nothing to do with the city institute or whatever. That's a difficult time. We
mm.
all had to go through it, and we all powered through it. That's more or less it. Yeah.
Absolutely. Absolutely. Love the way you approach the question with, some real life example. And I think that's the best part of today's session, I would say.
Yeah, I mean, like, it's there in every profession. You do. I mean, like, see, at the end of the day, you are a professional scientist, right? You do.
Mm,
You're not an amateur anymore. You do it as a profession. So you're a professional scientist,
mm,
right? So
mm,
any professional people in their lifetime do transit from one place to another, and they still do the thing that they are known to do. And
mm,
I mean, you can take a footballer going from one club to another. You can take a cricketer playing for an IPL team and then playing for the nation.
mm.
If you're a professional person, you do the same thing. I think it's very similar.
True.
It's no difference at all. So yeah.
Mm. I see. I
Yeah.
see. Cool. So we have so many, like, our major target audience is like bachelor's and master's student. So
Yeah.
maybe after this talk, you could also get some inquiries for internships and things like this. So I would really love to shortly brief about that. What are the day-to-day techniques that are done in your lab or maybe in this field, which would be useful for somebody to really start or maybe already in the intermediate phase?
So, see, I get this question a lot, but I
Mm,
also would say that it's very difficult to answer this question in our
mm,
perspective. Yes, I mean, I
mm,
can go
mm.
ahead and list you 10 techniques, right? But those techniques are not that important. I mean, I can say we
Mm,
do a lot of microscopy.
mm,
We do sometimes we do some rheology. Sometimes we do some image analysis. I can go on, right?
mm,
But the problem is
mm,
that those
mm.
are not important. I mean, if that is what
True.
you are looking for, then you will be stuck with the technique. The technique is just a means.
Mm,
It's like a
mm,
it's like a vehicle, right? For example,
mm, mm,
I think you should focus on a question. Since you mentioned an uh, uh, example, let's say
mm,
some of you are in Europe. So let's say
mm,
uh, you go to London, right? Uh,
mm.
and London has this beautiful double-decker red buses. Uh, are you going to London for the buses, or you're going to London for going to London?
Going to London.
Right. So my point is, techniques are just the buses. It will take you around the
Mm,
city, and that's how you enjoy it. But
mm,
your motivation is the question. So, what
mm,
is the unknown scientific question that should motivate you? Rather, techniques are just like,
mm,
this is another method of delivering it. I mean,
mm,
it doesn't
mm,
matter which plate you're eating from. The food should excite you. So,
mm. I
yeah,
see. I see.
yeah.
I
Techniques
think
are,
most of the students.
yeah, whatever you need to do to answer that question, you would do that.
Mm-hmm,
I mean,
mm-hmm,
think about this way. I know people keep saying
mm,
that we need to know what are the things I will learn. The thing you
mm-hmm,
learn in a research lab is not the techniques, is
mm,
how to think about a question scientifically, how to read a scientific things, how to reason some
mm,
things logically, and
mm,
how do you
mm.
build a logical scientific argument or hypothesis, and you test it.
Mm,
Either you
mm,
validate it or you negate that. So that is what you are
mm,
learning in a lab, right? Uh, Techniques
mm.
are means of validating or negating those hypotheses. So they can be
Yes,
whatever, right?
absolutely.
Yeah.
Absolutely. Sir, so like your work spans biology, physics, little bit of computational science as well. So like working in the interface of multiple field, like how do you approach a scientific problem? Maybe you can give a small example, a project running in your lab or maybe
Yeah, yeah.
already published story.
Yeah. So I will give you an example. So what we are very excited and motivated to
Mm,
look into is like how
mm,
like this three-dimensional complex environment regulate behavior of active living organisms in
mm-hmm,
this complex environment. So why do we do
mm-hmm,
this, right? So
mm,
if you think about like most of the living organisms, be it bacteria
mm,
across different scales,
mm,
right? Be it
mm,
bacteria, be it mammalian cells, be it what I was gonna be it like yeast or worms or whatever. You take an example,
mm,
and you will start to see that they navigate and live through extremely complex three-dimensional environment. And the idea here is that how do these properties of this environment actually affect the biological outcome of these organisms? So one way I
mm,
can think that, well, these biological organisms can sense the environment and somehow they can evolve
mm,
to fit into those environment. While that is
mm.
true, but there are many examples where the changes occur much faster. Is the purely physical
Mm,
environment can regulate significant biological outcomes without invoking any organism specific biology. So that's what we are interested in. And the example that I would give is that we started looking into how bacteria grow in a mucus-like environment, right? So what we did is we artificially created a 3D matrix that mimics the rheological properties, viscosity and moduli of gut mucus that people have measured before. Now, I put different bacteria in those two different stiffness environments, and we started seeing that there is a beautiful pattern that emerges that has nothing to do with very specific organisms or very specific growth rates or nutrient or something. What it depends fairly on the shape of the bacteria. So if you have elongated shape, you can extend your progenies into 3 dimension, and you should be able to grow in a much more elongated colony shape. So shape does actually give you a selective advantage. So rod-shaped bacteria are less affected by the change in the stiffness of the mucus compared to the spherical bacteria. So where I am not looking into any specific organism, specific biology here, but simply the shape of a bacteria governs how the stiffness of the environment can play a selective role in their growth. So these are the kind of question that we are interested in, how the mechanical properties of the microenvironment matter, how the physical properties matter, how the shape of the tissues matter, or like how different combination of mechanochemical cues change the cellular behavior and stuff like that. So now different
Really?
things require different things. For the bacteria project I just mentioned, we had to do rheology because I'm making the material, making the 3D matrix. We had to do a bacterial culture. We did a lot of standard microbiology processes. And then we also ran a Python agent-based simulation in Python to understand how shape matters. So, it has several different things into the same project. But if I am stuck with one technique, then my questions will not move the way we would like to move. Yeah.
So, just asking a very impromptu question. Is it difficult to find students who would fit in the area of where you're working? Or I would say, how difficult is it to find students?
See, if people are interested in the question, the methods are very similar for everyone, right? For example, you will never find a person who will have all this experience,
All these
right?
things.
I mean,
Yes.
you can hire a person or find a student who is extremely talented in microbiology. They have to learn how to do this, agent-based simulation. You can find a extremely good person who knows how to do computation or something like that, but then they have to learn how to culture the things. So either way, it is a learning experience for all of us, including me. There are many things that we do now in our lab which I have never done before. So so for all of us, it's a learning experience, and we all learn together. So it is so all I think is important to what I'm looking for. I think that's what you are. I think a person who is very excited and interested to learn and 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 motivated and basically dedicated to do whatever it takes to get get to the question, and open to whatever I need to learn, I would learn to get the question. That is the kind of person is the best person for the lab. Yeah. And people come from different scores of life and all of that. So people are from biology, there are people from physics, there are people from engineering in our lab. So There are multiple different sources. People are here.
Hmm.
Yeah.
So how do you envision this field, rapidly growing field in next 10 years, especially talking about Indian ecosystem?
Sorry, can you
Hello?
repeat that? I missed the question. Half of
Yeah,
it.
yeah, for sure.
Yeah.
Okay. So how do you envision, this rapidly growing field, especially in India in maybe next couple of 10 years or so?
Yeah. See, there are. I'm assuming you're asking about 3D bioprinting and stuff like that,
Yes,
right?
absolutely.
So again, there are different motivations in 3D bioprinting. Some
Mm-hmm.
people are trying to make artificial tissues. Some people are using to make model tissue systems. Some people are using it to build like grafts and implants. Um, I think those are the questions that will drive the thing.
Mm-hmm.
3D bioprinting as a research, as developing the technique, there are a group of people who are doing that, but there are also a group of people who are not actually working on 3D bioprinting per se, but they're using that technique to do very serious science in other fields. So I think that will also expand quite a lot very soon. Yeah.
Mm-hmm. Absolutely.
Yeah.
So, like reflecting on your journey as a scientist and also worked in different continents, like what are the three most valuable lessons you would like to today, tell students especially or communicate to students?
Well, it's very personal. Again, like
Yeah.
it. There are certain things work with you in certain ways.
Mm,
It is like it is like working out or going to a gym or something. Some people's routine doesn't fit other people, right? And as much as people publish this, like this is the best workout routine by this, so you know, it doesn't work. You have to find your own groove. But I think the one thing I think is super important is like I think in academia or even in research or science in general,
mm, mm,
I think the people who survive per se or who basically become successful or continue their journey in academia in whatever
mm,
word you want to use it, people use this kind of
mm,
words. I think these are the people who never give up. So
mm,
you may have a you some definitely things don't work out, and
mm,
in many ways it can be a research question, it can be a research topic, it can be uh,
mm,
like several years of failures can also happen. But the
mm,
thing is that you always have like you have to come back and do it again. And other thing I learned during my PhD, it's super important for me, at least this worked out. And I know
mm,
it might
mm,
not be possible in many settings, but for me,
mm,
what worked out is having side projects, right? So whenever
mm,
there are times when my major project was failing for like several months, well, I mean, it was not working out until I found what to do to like change this. Like, so
mm,
what was the wrong thing I was doing? It took certain times to
mm,
troubleshoot that. When I'm troubleshooting, I was working on another thing. So while I'm failing in one thing, I'm still doing some successful things in another thing. So
mm,
that kind of
mm,
balances out, and you always have something that is working out. While
mm,
it's absolutely possible that uh, every project should go through a patch where things don't work out. So, and that is very true for that is my way of thinking that how uh, things can work out even when there is a guarantee that there will be ups and
Mm.
downs.
Mm. I see. I see. I think these are really valuable tips, or maybe very minor things, but even me as a PhD student, sometimes we just ignore the side projects or something like this. But when
Yeah,
things
they're
don't
super
work in
important.
your main project, your
Yeah,
side projects become your
we
main
all are
project.
humans, right? We all are humans,
Mm,
and as much as we say that, even now, when you fail at something, you feel bad. I mean, you maybe
mm,
be mature enough to understand that this is a process, and then you say like,
mm,
okay,
mm,
we'll solve the failure, we'll solve how to
mm,
do it, but it is very human
mm,
to feel a little sad about it, and
mm,
that's okay. So then you have to, if you have a side project going on, or if you have another thing that you are doing on the side, when this is not working, you focus on that. At least in your mind,
mhm,
you still feel good about, like, at least I have done
mm,
something.
mm,
So I
mm.
think that is super helpful in many cases.
Absolutely.
Yeah.
So, like, now I would like to ask you one of the last questions, of the today's event, and then we would, also take up some questions from the audience. So the last question goes like, what is the favorite discovery so far as per you or for you? So I can give you some examples of previous speakers that they gave. Like one of the answer was like discovery of H plus and Cl minus ions. So the PI thinks that, this shaped the world or changed the world. And then some of them, they said the sequencing techniques, they changed the world, something like the PCR or something like this. So what as per you is a favorite discovery in science?
Huh. I have so many favorites in many, many things. See, these things are very
Maybe
biased because
you
if you
can
use
list a few.
something, yeah, if you use something, then either you are biased to say that that is your most important because that shapes your career a lot,
Yeah,
and
true.
or if you found something very new and you're like, oh, I never knew that it's possible, and
Yeah.
you're like, that's amazing that we learned all of that. So it's hard to say in that per se, but I, that is very hard to say actually. There are several things that I can think of. Uh, because I work with also bacteria and mammalian cell and all of
Mhm,
that, I
mhm.
think uh, I think what shaped the world in a sense so far, or in the futuristic world, are you thinking about? Like,
Maybe you can also say about the futuristic world.
huh?
If you have something in mind.
Hmm. No, I have things in mind, but it is very, very all over the place. Because I have favorite things in engineering, I have favorite things in biology,
Hmm.
I have favorite things in.
Maybe you can say about them if you want to. Maybe
So
list a few.
okay, okay. Let's put it one way or another. I think one of the most favorite thing that I think I'm learning now also is like how people can manipulate single cells, right? I know, uh,
Hmm.
right? There are many things like you can identify the heterogeneity, you can learn the
Hmm.
heterogeneity,
Hmm.
you can barcode them, all of that. But is that is a technological advancement on this, is that a fundamental
Hmm.
discovery that changed everything? Maybe not. This is not a fundamental discovery. The fundamental discovery will be how you can put like a few transcription factors and you can change the cell's state and fate, right? I mean, the invention of the Yamanaka factors that can transition cells into iPSCs. That
Hmm.
would be very interesting fundamental achievement. I can take a patient cell or anyone's cell, I can make a stem cell out of that, right? So
Yeah. Yeah.
many things are there. So then you can think about uh, like now you switch back and you can get into like this imaging techniques, and I'm very excited about all this like super resolution imaging that have changed the way
Mm.
we think about things. Now
Yes.
if you say like, well, super resolution is great, how about like you're thinking about structures inside a cell, how about structure of proteins? Well,
Mm.
now AlphaFold has made it very accessible to a lot of people
Yes.
to look into structures. So uh, I
Absolutely.
can keep going, right? So the
Yeah.
thing is that it's hard to point out one
Mm.
the most favorite thing to
Mm.
talk about, but there are several things that have milestones kind of thing. But
Yes.
yeah, but I yeah, I mean, many of them are very important right now. Some of them will be very important even after like 10, 20 years. There are some
Mm.
things that stay there forever. For example, like knowing the double helix structure of DNA.
Mm. Mm.
The fact that DNA is a double helix structure, that is a milestone, a thing that shaped a
Mm.
lot of different ways of thinking and stuff. So many ways you can pose this question. Some are technological, some
Mm.
are fundamental, conceptual, some are achievement because of the way we think about this. Some are using alternative techniques to understand some things. So yeah, I think like you can go on and on, but uh, it's very hard to point out in one.
Absolutely.
Yeah.
I agree on this. I agree on this. Okay,
Yeah.
so now we would quickly, we have a lot of questions from audience, but I'm very sorry I cannot take all of them due to time constraints. So I would pick and choose few of them, right?
Sure.
So Harshita is asking that how close are we to printing a fully functional organs, and what are the main scientific barriers remaining?
Uh,
I think they
depends on
have.
what you call an organ, right? If you
Hmm.
say my organ is like a bladder or something, which is based,
Hmm.
or skin also, which is
Hmm.
basically a layer of an ECM and some cells, right?
Hmm.
I think you can make that
Hmm.
pretty easily. People
Yes.
have, I, if I'm not wrong, people have done 3D
That
printed
is.
skin grafts and have implanted that
Yes.
as well.
Hmm.
So if you consider, I mean, and that is also an organ, right? So skin is the largest organ in our body. So if you consider that, yes, we are doing this. Now, I think what you're asking is about making something a complex organ, for example, kidney or
Yeah.
liver, or like a heart or even brain or something. I think that will require more work to be done. A simple example is like that my PhD advisor also used to say all the time, but I would
Hmm.
reiterate whatever he used to say is that, look, we the major technological, so the 3D bioprinting is a technological advancement, right? You need to figure out how to put together things and they should work out together. So the major place where we made those kind of rapid technological advancement is going making your telephones or like laptops, right? Used to take like a room to make a computer. Now your laptop does a
Hmm.
better job than that. So the fact
Hmm.
that we understood how to make those microchips, each and every single
Hmm.
part, and make them with precision, that was the key to put it together in this, even in this complex
Hmm.
circuitry. I think
Hmm.
if you break down the individual parts of an organ that is needed, like uh,
Hmm.
we need to understand how to make this like really folded structures, really. So all of these
Hmm.
complexities, different cells, different curvature, different manifolds, different interpenetrated architectures with different types of cell, uh, and
Hmm.
allowing them to self-assemble in their most normal configuration is the
Mm,
key. I think those individual questions are being asked in many different contexts now, or
mm,
they need to be developed in future. So I think that is
mm,
the structure and 3D printing technology we can improve. There's no I think that there is no doubt in that. But also, like, this basic fundamental of biology in those 3D architecture is super important to understand to
mm,
eventually go and have an functioning organ or something.
mm. I see. I see. Okay. So Om Saswat is asking that what do you think about how far are we in replicating disease? And continue with, have you ever thought of replicating chemokine gradient mediated mucus secretion? Because it's Boyden chamber method used today. I think I don't get this question too much, but I think you will definitely understand it.
I didn't get the first question. Is it like how close are we creating disease? Uh,
Replicating the disease,
Replicating the
replicating the
disease
methods in the in vitro system.
to understand how disease system works and stuff.
Hmm,
Well,
hmm,
people
hmm,
routinely do like mouse models to understand cancer tumors and stuff, right?
hmm,
So
hmm, hmm,
uh,
hmm.
uh, now 3D organoid system models are also cancer
Yeah.
organoids are also used to understand cancer. So I'm not gonna say I think we are almost using some of those techniques, and not only in research settings, like even like pharmaceutical companies are also creating 3D bioprinting liver tissues to test their drugs and stuff. So I think that is fairly there. It is being improved, and people will keep improving this, and more you will see people are using those techniques. So that
Mm-hmm.
is there. But then the second question was, have we ever used a chemokine gradient to secrete mucus? We haven't done it. People have set up like a chemokine gradient for
Hmm,
mammalian cells, for bacteria, and people have studied how cells deposit ECM in different gradient conditions as well. So
hmm,
I think
hmm,
that kind of work is already there, uh,
hmm,
especially in terms of like cancer cells and those migration of cancer cells. People have done those. We don't
hmm,
quite do that kind of work, but there are other people who do those kind of things. I might be wrong, but I think there are several studies where people have
hmm,
looked into that.
hmm, hmm. I see. So Harshita Singh is asking, like, like how can we use this in for personalized medicine? What are the potential applications of the in vitro work that you are currently doing? And also, I would just take up one more. How to ensure vascularization in bioprinted tissues? I think this is more towards.
So I'll answer the first one before. So
Mhm,
vascularization
mhm,
is a major challenge, right? So
mhm,
because the tissue needs to be fed. There are techniques people use by putting like endothelial cells in the 3D printing structures,
mhm,
and they self-assemble. They create like this micro channels,
mhm,
microvasculatures, and that allows nutrient to flow. So people do that, but there are it is still an active area of research how to create
mhm,
designer micro vasculature inside a
mhm.
tissue. So let's leave it there. But the first question was, sorry, what was the first question again?
So the first question is that, like, how can the in vitro
Oh,
work
personalized
used for
medicine.
the
Yes, yes, yes.
personalized
Yeah.
medicine?
So, see, I will give you an example. Like, let's say you can create like precise tumor organoids or tumor models of in vitro system. One
Mm.
can check what kind of combination of drugs can actually cause apoptosis in those cancer tumors. How you can target those tumors. What are the kind of sort of markers that you can target on those cancer tumors. So that might be very different from patient to patient, or not, but those are the kind of things you can try seeing, like what happens to those. For example, most of these drugs are being tested on liver tissues. People look into those and see like how these drugs can affect, or you can take a regular drug and you can put those in a healthy liver tissue that you have created or something, and see if that is going to cause any damage or defect on the liver. So depends on the question. Those are more application based. So depending on the application, that can be used uh, generally. But you can also think about this way. You can this kind of approaches may help you to understand the disease more cleanly, for maybe not quite so for medicine directly, but it will help you to understand the disease more cleanly. For example, if you're looking for cancer cells and you go through this different in vitro 3D methods, you may be able to tell whether this cancer is more invasive or less invasive, right? If you can put them in different 3D matrices of different stiffness that mimics different organs, you can understand whether they will grow better or less in this kind of stiffer tissues or less stiffer tissues. You can change their environmental pH and understand like whether they will survive in this kind of body environment or not environment. These are the kind of questions you can answer using in vitro systems.
Absolutely. Great. So I think we cannot take all the questions today, but we have feedback form, you know, and you can really fill your questions there, and we would get in touch with the speakers, and few interesting questions you can answer us by email today or later,
Yeah.
right? Yeah.
Yeah.
So, it is very important to fill the feedback form, especially for our audience, because, by this, we would also grow. And at the same time, we would know what to improve in our setting. So, because we also know we're not doing everything perfectly. So, this helps us a lot, right?
Great.
So, now I would like to request Bhakti to please deliver vote of thanks for today's event.
Yes, it is my privilege to extend a heartfelt vote of thanks on behalf of all of us here. First and foremost, I would like to express my sincere gratitude to our esteemed speaker, Dr. Tapomoy Bhattacharjee, for sharing their valuable insights and expertise with us. I would also like to thank all my teammates for their efforts in putting together this event so seamlessly. From coordinating the schedule to
Mhm.
ensuring a smooth flow, your dedication behind the scenes has made this webinar a success. A special thanks goes to our audience. Your active participation, insightful questions, and enthusiasm have truly enriched the session. It is your engagement that drives the success of events like this. Once again, thank you all for being a part of this wonderful session. Let's continue to think, grow, and share together. Have a great day ahead. Thank you.
Thank you. Thank you so much. Thanks for having me. It was a great discussion. Thank you for,
Thank
uh,
you.
yeah, thank you.
I really loved hosting you today. I think.
Yeah. No worries. Thank you for having me. I hope to hear back soon. See you. Bye.
Bye bye.